Welcome, engineers! Today, we're diving deep into one of the most critical challenges in building global-scale applications, cross-region data synchronization. As our users spread across continents, ensuring data consistency and availability becomes a complex dance. This isn't just theory, it's about building systems that gracefully handle real-world chaos, like internet cables getting cut or users in different time zones editing the same content. By the end of this lesson, you'll gain a solid understanding of the mechanisms that power global platforms, enabling you to design more resilient and performant architectures. Specifically, by the end of this lesson, you'll be able to, first, understand the challenges of global data synchronization. We'll unpack the inherent difficulties that arise when data needs to live everywhere all at once. Second, you'll be able to explain asynchronous replication and its trade-offs. This is a cornerstone technique for achieving speed and responsiveness in distributed environments, but it comes with important considerations. Third, we'll cover how to describe conflict resolution techniques in distributed systems. When multiple users modify the same data concurrently across regions, you need smart strategies to merge those changes without data loss. And finally, you'll be able to identify strategies for handling network partitions. Because in a global system, network failures aren't an if, but a when. Let's get started on building bulletproof synchronization systems. Let's kick things off with asynchronous replication, a fundamental pattern for global systems. Imagine sending a WhatsApp message across the world. You get an instant sent confirmation, right? That's asynchronous replication in action. The core idea is that asynchronous replication enables fast local writes. When a user performs an action, like posting a tweet from California, their local region immediately accepts that write and responds quickly, giving them instant feedback. This is crucial for a smooth user experience. Meanwhile, in the background, data propagates globally. The update doesn't wait for confirmation from every other continent before confirming to the user. Instead, it's queued up and sent to other regions like Europe and Asia in parallel. This approach prioritizes user experience over immediate consistency. For social media or messaging, users care more about their action being acknowledged instantly than every single data replica being perfectly identical at the exact same millisecond. The main trade-off is eventual consistency for lower latency. Your friend in Japan might see that tweet a few hundred milliseconds later, but the user who posted it experienced almost zero delay. This trade-off is often acceptable, even desirable, for highly interactive applications, ensuring responsiveness for millions of global users. While asynchronous replication is great for speed, it introduces challenges, especially when multiple users modify the same data simultaneously across regions. This is where conflict resolution comes in. Think of Google Docs, two people editing the same paragraph from different countries. Google Docs doesn't crash, it intelligently merges their changes. Similarly, in our systems, conflict resolution merges simultaneous data changes to ensure a coherent final state. A key tool for this is vector clocks, which track the causality of events. These aren't just simple timestamps. They're logical clocks that help us understand the happened before relationship between operations, even across different regions. Based on this causality, we employ various strategies like last writer wins for simple cases, such as a profile update, or more complex merge strategies for intricate data like follower lists. It's about defining rules for how conflicting updates should be combined. But what happens when the network itself fails? Submarine internet cables get cut every year, isolating entire regions. Your system must be prepared for this. Network partitions require independent operation and later reconciliation. This split-brain scenario means regions must continue functioning autonomously and then intelligently reconcile their data once connectivity is restored. It's a critical aspect of building truly resilient global systems. Now, let's look at the architectural components that make this global synchronization a reality. We're talking about a distributed nervous system. At the heart of each region, we have region coordinators, which manage local operations and replication. They are the gatekeepers, accepting local rights, attaching vector clocks, and scheduling updates to be sent to other regions. They also detect network partitions. Then there's the synchronization engine, the brain of our system, which implements core logic. vector clocks, queues, and resolution. This component is responsible for generating and comparing vector clocks, managing asynchronous replication queues for outgoing data, and executing the conflict resolution algorithms we discussed. To keep an eye on everything, we have consistency monitors, which track system health and lag across regions. These monitors are crucial for observing replication delays, the rate of conflicts, and the progress of recovery after a network partition. The overall cultural flow for an event like a tweet follows a clear path. It starts with a local write, where the user's region immediately accepts the data. This is followed by asynchronous replication, where the update is queued and sent to other regions. And finally, if needed, conflict resolution ensures all regions converge to a consistent state. This structured flow ensures both speed and eventual data integrity. We've covered a lot of ground today, and I hope you feel more equipped to tackle the complexities of global-scale systems. Let's quickly recap our journey. First, we established that global systems demand robust cross-region synchronization. Simply put, without these mechanisms, your application can't truly serve a worldwide audience reliably. Then we explored how asynchronous replication balances speed with eventual consistency. This trade-off is often the secret sauce for delivering a responsive user experience in a distributed environment, even if it means a slight delay for remote users. Crucially, we learned that conflict resolution and partition handling are crucial for resilience. Building systems that can intelligently merge conflicting data and gracefully recover from network outages are hallmarks of a robust production-ready architecture. By understanding these patterns, you're not just learning theory, you're gaining practical insights into how platforms like major social networks or collaborative tools operate at scale. To help solidify your understanding, here's a thought experiment. How would you apply these principles to a real-time collaborative application like a shared whiteboard or a code editor? Think about how you'd handle conflicts and ensure a smooth experience for users editing simultaneously from different parts of the world. This exercise will deepen your grasp of these powerful concepts. Keep building, keep learning,